everybody, welcome back to Monte Carlo Methods. It has been a long time since I filmed a video, and I'm not sure anyone who started with me is still here, but hopefully you're watching this in the near future and you have a complete series to watch and to skip ahead as you like. The reason I stopped was I had sort of an existential crisis after my last video about what this series was going to be. The video was quite long and I wanted it to be more snappy, 15, 20-minute videos at most, but I can't let go of the rigor. I thought a lot about putting the rigor in a separate video. There were problems with that as well. And I also hate talking about random number generators, and I kind of think you do too. We all want to get to the exciting simulation and not testing the underlying random number generator, but the guilt is real. It's all based on the random number generator, and I don't think I can skip this. But if you're watching this in the future and I have more videos, you can skip it. So today I'm going to continue talking about testing random number generators. In our last video, we talked about a runs test. We had values spit out of our random number generator, and we looked at like how long we get a run of increasing values and a run of decreasing values. And if they're truly independent, we shouldn't see them get too long. Today's test is another runs test. This test, as the last test, is not really worth anything on its own. For example, if you're trying to test whether or not your sample comes from a uniform 0-1 distribution and you say, I know that the mean of that distribution is 1/2, and you do a test and you pass a test to say that for your generated numbers, it appears that the mean for the underlying distribution is 1/2. That doesn't tell you anything about uniformity or independence. That just can help you maybe knock out uniformity, if your mean is very far away from 1/2. So any one of these tests alone is worthless. They should be put together as a whole suite of tests. And also keep in mind that they are hypothesis tests. So there is type 1 and type 2 error, and they are all based on central limit theorem approximations. So there's even more error there. So don't freak out if you fail a test. But if you keep failing it repeatedly and fail multiple tests repeatedly and fail them in sort of the same direction, like your value you computed is always above where it should be, not sometimes above, sometimes below, something like that, then maybe you have something to worry about. So in today's test, it is a test for independence, but it does depend specifically on the underlying distribution. You can do this for any distribution. We're just going to do it for the uniform. I have no reason to do it for another distribution. We're going to have different tests later, like if you simulate from a gamma distribution, how to show that those values came from a gamma distribution. We have better tests to do that more directly. Today's test for independence, again, depends on uniformity, and we are looking at runs of numbers above and below the mean. The mean of the uniform 0-1 distribution is 1/2. It's right in the middle. And let's look at these values. These are the first 21 values from a sample I took of size 100,000. As before, the order is important. This is my first value, second value, third value, fourth, fifth, etc. So we're going across the rows. This first number here is below 1/2. It's below the mean. So we're starting a run below the mean. The second number is still below the mean, so we're still below the mean. So is the third, but the fourth number is above the mean of 1/2. So here is a run of length 3 of numbers below the mean. For today's test, I actually don't care about the length of these runs at all. I just care about the number of runs either above or below the mean that I can find in my full sample of size 100,000. So if you want to screenshot this just to check the count, I see on this screen a total of 11 runs, and there are 5 above the mean and 6 below the mean. And then for the other values in my sample of size 100,000 that I'm not putting on a slide for you, I got a total of 50,187 runs above or below the mean. The question is that good? Does that bode well for independence and or uniformity? Let's let x1 through xn be a random sample from some distribution, and let Rn be the number of runs above or below the mean of that distribution. What do we expect Rn to be if we're really talking about independent values from a uniform 0-1 distribution? Before looking at the runs, let me just remind you that if you have a random variable x that has this uniform distribution, the mean is right in the middle, it's 1/2, and the probability of being above or below the mean is also 1/2. This is not true in general. For example, if we have an exponential distribution with rate lambda, The mean is 1 over lambda, and the probability you're below that mean is 1 minus e to the negative 1. So don't confuse a mean with median, although they are the same if you have a symmetric distribution. So a median is a value that cuts the area under the PDF in half. A mean is more like a balancing center of mass point. But back to our test, this test is going to be specific to the uniform 0-1 distribution. So suppose we have x1 through xn, a random sample, from the uniform distribution on 0-1. In random sample, we have independence as part of that definition of a random sample. So if these are truly independent and from a uniform 0-1 distribution, let's count the runs above and below the mean by using indicators just like we did before. So for I going from 1 through n, I'm going to let I sub I be 1 if x sub I starts a run either above or below the mean. And then I'm going to let r sub n be the sum of all the indicators. That will give me the total number of runs above or below the mean. To find the expected value of r sub n, I could take the expected value of this sum. Expectation is a linear operator, run the sum through. We need to compute these individual expected values. The first indicator is always 1. So it's not really a random variable, or you can think of it as a very boring random variable. It's going to equal 1 with probability 1 because the first value always starts a run somewhere above or below the mean. The nth value can actually start a run here, whereas it couldn't in our previous test for increasing, decreasing runs. So imagine this is the very end of your sample of size 100,000. Here you can see we're coming in above the mean, but the very last value is below the mean, so it is starting a run. Whereas our other test had a lot of dependence between, increasing and decreasing involves looking at two numbers at a time. So last time we had that IN was 0, but we don't have that here. What is the expected value of IN? As you know, the expected value of an indicator is always the probability of the thing being indicated, in this case, the probability that xn starts a run above or below. This can be written as a sum of two disjoint event probabilities above the mean and below the mean. So the probability that xn starts a run above the mean or probability below the mean, we're going to add those probabilities. If xn starts a run above the mean, that means that xn needs to be above the mean. And also because it's starting that run, it means that xn minus 1 needs to be below. And the other way around, if xn is starting a run below the mean, it needs to be below the mean, and the one before needed to have been above the mean, or xn would just be continuing a run below the mean, it wouldn't be starting one. Now, these are assumed to be independent, so I get to factor all of these probabilities, and these are all supposed to be, in our hypothesis, IID uniform 0-1 random variables, so all four of these probabilities are 1/2, and when you multiply those and add them together, you get 1/2. So now we know that our I1 is always 1, and therefore the expected value of I1 is always 1. We know the expected value of IN is always 1/2. Let's look at the other indicators. As I goes from 2 to n minus 1, the expected value of I sub I is just the probability that xi starts a run. And as before, we can break this up into two disjoint event probabilities, the probability that xi starts a run above the mean, plus the probability it starts a run below the mean. And I'm going to do a very similar thing. I'm going to write out what this means. If xi starts to run above the mean, then it needs to be above the mean. And the previous value needed to have been below the mean, or it wouldn't have started at xi. So we get we get exactly what we had on the previous slide. And we can use independence to break up these probabilities into products. Because they're all uniform 0-1, all of these probabilities are 1/2. And again, we get the expected value of the indicators is 1/2. I sub I when I goes from 2 to n minus 1. So to put this all together, the expected number of runs above or below the mean is written as the sum of the indicators in here. We run the expectation through. The first value here is 1, and all the other values are 1/2. So there's n minus 1 additional values after you knock off the first one. So we get 1 plus n minus 1 times 1/2. Put that together, you get n plus 1 over 2. When n is 100,000, as it was in our sample, this expected number of runs above or below the mean comes out to be 50,000.5. And I'll just remind you that in our sample, we observed 50,187 runs above or below the mean. So the question is this close enough? To figure that out, we want to look at the distribution of Rn. On average, we know what it should be, but how sort of variable is it around that value? Is 50,187 significantly larger than 50,000.5? Because our Rn is a sum, we can again use the central limit theorem on this problem as an approximation to the distribution for R. So we're going to use normality here. In our last test, we had a lot of dependence, so we had to use a specialized version of the central limit theorem that allowed for you to be talking about dependent variables. This one's actually easier. I claim that these are independent once you get rid of the first one. So let's put I1 aside. I claim that the rest of these are independent. And that may seem believable, it may not, because starting the run depends on what happened on the last one. So to prove that these are independent, I need to look at joint probabilities for I sub I and I sub j. They can take on the values 0, 0, 0, 1, 1, 0, and 1, 1. I need to look at all these possibilities and see if they factor. And I need to do this for different types of I and j, because we're going to have different things going on maybe at the endpoints when little I and little j are 1 or n, and maybe something different going on when I is I and j is I plus 1, rather than having two indicators that are far apart in the series. So I'm just going to check out a couple of values here, and a couple of these probabilities we're going to show they factor, and I'm going to leave the rest to you. Consider the joint probability that the first indicator is 1 and the jth indicator is also 1, where j is some number greater than 1. The first indicator is always 1, so this is meaningless information here. It's like saying, what is the probability that x is 3 and also 2 is less than 5? That's just the probability that x equals 3. In other words, I'm going to drop this. This is just the probability that I sub j is 1. On the other hand, the probability that I sub 1 is 1 times the probability that I sub j is 1. This one has probability 1. So this product is also the probability that I sub j is 1. This is equal to this, so this is equal to this, so we do have that factoring. I said I wasn't going to do them all. I'm certainly not, but that was a really special case here. So let's look at an I greater than 1. And I think that you would have no problem believing that if you look at some xi starting a run and some other xi way down the line starting a run, I think you could believe those are independent, but right next to each other, not as clear. So I'm going to look at the joint probability that the ith indicator is 1 and the I plus first indicator is 1, and hopefully this will factor into the product of the individual probabilities. So if these are both 1, that means that xi starts a run. This a slash b means above or below run, and x sub I plus 1 starts an above or below run. We have 4 cases to break this into. They are disjoint. So x sub I can start an above run, and x sub I plus 1 can start an above run. Now, maybe you already see what's wrong with that one, but writing out these 4 cases, this is what we get. And then this is just a depiction of these 4 cases. So these A's and B's stand for above and below, and an A in the ith slot means that xi is starting an above run. So this is xi starting an above run and x plus I starting an above run, and that cannot happen because this means you're above the mean, and then you're above the mean here. You're not starting above the mean. You need it to be below and then start to be above the mean. So you can't start a run above the mean and then start another run above the mean in the next value. The probability associated with this event is going to be 0. The same thing is true for this event here. If xi starts a run below the mean, then that means the number before that was above the mean and xi was below the mean. And xi plus 1, if that's below the mean, it's not starting a run. It's continuing a run below the mean. So this can happen either. And we're left with just 2 out of 4 probabilities we need to compute and add to find the probability that I sub I is 1 and I sub I plus 1 is 1. Let's look at the second one. If the ith x is going to start a run above the mean and the I plus 1 is going to start a run below the mean, then we necessarily need the value back here to be below the mean, or the ith one would not be starting that run above. So we need something like this to happen. Similarly here, if x sub I is supposed to be starting a run below the mean, we need the value before that to be above the mean, or it wouldn't be starting that run at the ith index. So pulling that all together, the joint probability that I sub I is 1 and I sub I plus 1 is 1 can be written as the probability that the I minus first value is below and the ith value is above and the I plus first value is below, plus the I minus first value is above and the ith value is below and the I plus first value is above. And these are all independent uniforms under the assumption of what we're doing here. We're doing a hypothesis test where we assume this stuff is true and do computations, under that assumption. So I get to break these probabilities up into a product, and they're all 1/2. So you get 1/2 times 1/2 times 1/2. plus that again, which is a total of 1/4. We have shown that this joint probability does factor into the product of the individual ones because we've already seen the probability that x sub I is 1/2, and the same for x sub I plus 1. So 1/2 times 1/2 is definitely 1/4. This is not enough to establish independence. We're just looking at I and I plus 1, so not more generic I and j subscripts. We're just looking at they're both equaling 1, not 1 and 0, 0 and 0. There's many cases we have to look at, but this is how you start the road to showing that they're independent. And you could avoid this. You can say, I'm not going to believe they're independent, but when you compute the variance you need, you're going to need to compute some covariances. They're going to end up being 0, which we know they're going to be 0 now because we know we're dealing with independent things. So you're going to end up doing the work down the road anyway. Okay, so we have established or begun establishing and know how to establish the independence of I2 through IN, those indicators. The number of runs above and below the mean is written as 1 plus the sum of the remaining n-1 indicators. And we know the expected value is n plus 1/2. And because these are independent, we can use the plain old central limit theorem. We don't need anything weird for dependence to say that in the limit, as the sample size gets large, this sum is going to look normal, and a constant plus a normal random variable is still normal. So what normal distribution are we talking about? The mean for Rn is n plus 1/2, and we're left with having to compute this variance. The variance of Rn, I'm just going to plug in what Rn is. So if you add a constant, a number, to a random variable, that doesn't affect the variance, right? If you're talking about the variance of an x, it's how spread out it is. And if you look at x plus 5, you're still talking about how spread out it is, just in a different location. So adding a constant like this does nothing. We can drop it. Because we have established independence, we can pull the sum out of the variance. If you haven't established independence, the variance of this sum should, in the next step, be written as a covariance of the sum with itself. Let's look at the variance of I sub I when the subscript I is 2 or greater. We know that the expected value of I sub I is 1/2, and the expected value of I sub I squared. So this random variable is 0 or 1. When you square it, it's still 0 or 1. This is the same thing as this I sub I squared is the same thing as I sub I. This is 1/2 and this is 1/2, so we get 1/2 minus 1/2 squared, we get 1/4. Going back up here, we have 1/4 n minus 1 times, so we get n minus 1/4, and we have completed the mean and variance. Our number of runs above and below the mean is approximately normally distributed by the central limit theorem, with mean n plus 1/2 and variance n minus 1/4. So if we think of this as approximately a normal random variable, if we subtract the mean and divide by the standard deviation, the square root of this variance, we should get something that is approximately normal 0, 1. For the normal 0, 1 distribution, the nice bell curve centered at 0 with variance 1, we typically look at putting 5% of the area out in the tails for this sort of hypothesis test. Like, where is Rn supposed to be? Well, this Zn is 95% of the time between the numbers negative 1.96 and positive 1.96. So if I plug this whole thing in for Z and kind of solve down for where Rn should be, we expect Rn to be between n plus 1/2 plus and minus 1.96 times the square root of n minus 1/4, approximately 95% of the time. This is error in hypothesis testing. This is approximation due to the central limit theorem. This is not exact. So for my sampled values, my realization of this random sample of size 100,000, I got 50,187 up-down runs, and I have the value of n being 100,000. I can compute these endpoints, and I get 49,690.6 and 50,310.4. So in fact, my sampled value of the number of runs, which was 50,187, does fall in this interval. So I pass this test for independence with a little bit of uniformity mixed in. It's not independence independent of uniformity. It's just bolstering the idea that things are okay with my random number generator. I've said it several times in this video, but I can't say it enough. 5% of the time, you're not going to be in the right interval. Probably more because of the approximation we're using. The smaller your sample size, the more you're going to be not in the interval. And this is a test for independence that sort of is mixed with uniformity. It should not be used alone to establish either. So the next test we want to talk about is we want to look at the length of those runs above and below the mean, like our first one for our sample had length 3. And we need to figure out sort of the expected number of runs of length 1 above and below the mean, the expected number of runs of length 2 above or below the mean, and length 3, and so on. And we're going to categorize things, and we're going to use a chi-squared goodness of fit test. So our next video is going to be a chi-squared goodness of fit test video. It's a fill the gap video. It's not going to involve simulation or random number generators. And then in the one after that, we're going to do this test, and we're going to move on. And we're eventually going to start simulating things. So I hope to see you in the next one.